Okay, I think our session is recorded. So good day to everyone, no, for the EE A131 students, no, for power system operations. Now we are now on our next topic, a very good topic, the continuation of part 6, which is load flow analysis. Now, just a recap what we have discussed, no, on load flow, no, analysis in part 6. We just discuss what is load flow all about. We use the algorithm for Gauss-Seidel, some sample problems, and also the types of buses that we use, if that is a slack bus, PV bus, PQ bus, right? And then from there, we use some the algorithm of Gauss-Seidel, or the method of successive substitution, in order to get the load flows. But there's a limitation, on that method, because that method, is definitely, if you have a very large system already, it will become ill-conditioned. When I say ill-conditioned, a parameter that is changed, on some of the parts of the power system, the rate of change is also, very large. So you trick a little bit of parameter, and then the changes becomes very large. And that will be the case. Then it will become divergent. And if you still use method of successive substitution, it will give a very big part of the memory capacity, and then many iterations. It will give many iterations until it converges. But if you already have the idea of having Newton Raphson, in terms of the convergence of getting the root, you see the bigger difference, in terms of the solution part. It converge very fast, so that in this case we need to do that on this topic, because this method, or the NRLF, or Newton Raphson load flow, is the best type of numerical analysis solution for a non-linear equation, which is very practical in solving in larger power systems. So ito yung ginagamit, the typical solution, which is the NRLF. Okay, there are many types of solutions that I told you from the introductory. It can be fast decoupled, but anyway, the principle itself is based on NRLF. And please take note, this type of theory, or this method is already existent way back 1930 to 1930s, 1950. Ang problema lang is the memory, yung capacity ng PC. The theories that you see here are very, very old. But again, old school is pretty school. So it means that if you know how to do this, you can also already understand the other load flow solutions. So there are many load flow solutions. I already give you the Gauss-Seidel, the basic, and then the most practical, which is today, Newton Raphson. So please bear on some of the mathematics here, a very tedious solutions, but again, you can use computers or even your math labs solving some of the numerical solutions here, or even the partial integration or the matrices. Okay, let's move forward to the theory part. Okay, now as I mentioned, the limitations of the Gauss-Seidel method, it is prone to divergence, because any rate of change will give a very big difference on the solution part. Please take note, a power system is a quasi-state, which means it dependent on time. If the time is in terms of millisecond, microsecond, any change on that, voltage, frequency, current, it also change the state of the equations. So that's why power systems is a very complex solution in terms of the numericals analysis, simply because any change will give a abrupt change on the matrices, so it will become ill-conditioned. So for a larger power system, Newton Raphson is found to be more efficient and practical. So the number of iterations to obtain in a solution will be dependent on the system size, but more on the functional evaluation in each iterations. So here you will expect some partial differentiation, as I mentioned, which will form the Jacobian matrix, which is very important in getting the roots, or in terms of the currents, angles, voltage, etc., which is dependent on the condition. Okay, now let's move forward to the introductory part, wherein we already described this equation here by, by nodal analysis, no? By using the Poisson-IV technique, no? But again, it is already generalized, this one. Whatever the current that is flowing here will be the current that is flowing, no, to the mutual buses and to the shunt buses. Ito yung bus number mo. This is your ith bus. And V1, V2, and Vn to the here are the mutual buses. And then so you have your series admittances, which is designated by yi1, yi2, yin. Now you can have this general form here, but there will be a much general form on the next slide. No, you can, if this is j is not equal to I in this case, but again, no, this is derived on KCL using the Poisson-IV relationship. I is equal to V times Y. Now, no, it can be rewritten in a much practical way. If you can still recall, no, your Y matrix in terms of your YII and YIJ, and YIJ is negative YIJ here, and this is your self, and this is your mutual. And again, your self is summation of all of the admittances connected to the bus I. Okay, so you can have this relationship. Now, it must be in polar form. When I say a polar form, no, if you have a current, no, in terms of phasor, no, it can be represented by two things, magnitude and direction part, right? Minus or plus in this case. Now, in this manner, we can represent this equation here in terms of a polar form. So kapag polar form na, if you, for example, you have your current I1, theta 1, no? If I multiply it by current I2, theta 2, di ba ang lalabas dyan, I1 magnitude, multiply by I2 magnitude, and then the angles will be added, right? Theta 1 plus theta 2, right? That's the identity there. Kaya nga nangyari, what happens here is it becomes like this. Now we also discussed, no, the SLFEs, if you can still recall, no, your Gauss-Seidel technique, no, second video lecture there, wherein, no, if you have a Pi minus JQI there, that is simply equal to V conjugate I, which is I tell you that, no, we have voltage reference and current reference. We use here no voltage reference because we use nodal, and it will become like this in terms of a lagging condition. Now we can still simplify all of these things. It's just a recall on what we have discussed, no, on Gauss-Seidel method or technique, or getting the SLFE, so slack load flow equations, slack load flow equations. But we can substitute equation 1 and equation 2, no? Wherein your current I here, substitute it here, definitely, it will become like this. Okay? Please take note, kaya ito naging negative I simply because of the VI conjugate here. Okay? Now we can clear this out. Moving forward, no, it will become like this, and you will add, no, the angles of your voltage and your admittances. Okay, please take note, by the way, before we proceed. The theta here, please take note, that is represented here, no, along the way, is the angle of your admittances connected. Admittances. Your alpha here, no, is the angle of voltage of your voltages. Okay, now, this is the, no, general form. But again, no, it's much practical that you need to break down, no, the real and the imaginary parts. Right? So parang this is the same thing with the Euler identity, right? It can be broken down, no, the Z bar theta, considering Z is the magnitude and theta here is the direction part. It can be broken down to a real and imaginary parts, right? So don't forget the Z here, no? Ayan. Diba? It can be broken down to its corresponding, no, real and reactive part. Cosine means real, sine means imaginary part. Please take note, don't forget the negative here, no? Because it is negative there, no? In terms of the magnitude of your Q, right? So equations 3 and 4 is very important, okay? Because you just break down the P and Q respectively. These are the powers and reactive powers connected at a certain bus. Okay? So we just recalling some of your mathematics here. And please take note if you see some difficulty in how it is done. So just recall your advanced math in terms of matrices. Okay, now you have 3 and 4 here based on this general equation. Okay, let's move forward. Just bear the mathematics on the next few slides. Equations 3 and 4 constitutes a set of nonlinear equations which is dependent on variables. Okay, here we have two equations in the load bus, in equations 3 and 4, and one equation for the voltage control bus. You already know the difference between the two because we have already described that one on Gauss-Seidel method on the second video that we have. Now, we need to expand this one in terms of Taylor series. Okay, I will not go to details what is Taylor series all about. But it's very important in order to have an initial estimate, which is we neglect all of the higher order terms and we can simplify things up. And it will result on the following equations, which is very important in the Newton Raphson method. This equation. Okay, so don't be surprised, that you can have these equations here with the partial derivatives, as you can see, and it is being simplified using a Taylor series. Okay, please take note of the following, the change of the powers here in terms of P and Q respectively, and we have the matrices in terms of the partial derivatives of the power in terms of the corresponding angle of the voltage. Please take note that we already did not incorporate the slack bus powers here. Kaya we start at 2 because the one here is reserved for slack bus. Okay, now we have the partial derivatives of the power in terms of voltage, partial derivative of the reactive to the voltage angle. Please take note, alpha is voltage angle. Partial derivative of your Q2, or your reactive to voltage. So please take note of the following. Okay, that's 1. Ito naman, P2 to, in terms of voltage 2. Okay, divided by, partial derivative of Q in terms of the angle, magsisimula sa 2, definitely. So this is just a mnemonic, for later, discussion. Yeah. Okay, real reactive powers. And please take note what we have developed here. And this is the change of the angles and the change of the voltage magnitude. Okay, because at the end of the day, we can solve those voltages and those angles. As you can still recall, yung Gauss-Seidel, diba? Method of successive substitution, we have voltage 1, which is definitely your slack bus. We start at voltage 2. And then whatever the voltage at 2, will be reflected at 3, And then uulit ka na naman ulit at voltage 2 if the tolerance error did not achieve in a certain way, right? So you substitute until you reach the tolerance error. Now, in this case, since we're considering Newton Raphson, it must be changed. And we can solve that voltage magnitude and the particular angle at the bus, at this using this method. Okay, so for that, it's very clear that we need to have this format here. Okay, and please take note, the slack bus is assumed to be bus 1, and the Jacobian matrix gives a linear relationship between a change of the voltage angles and magnitudes. Kasi given na halos lahat yan on our it will be derived on our problem. At ito yung masosolve natin. Okay, we can erase some of the particulars here. So we have an example later, don't worry, and then understand the process after that. So our main goal here is the platform or your algorithm and how you will deal with this. Okay. Now, in this equation that you see, you have the change of P and change of Q. These are the so-called Jacobian matrix because this one can be evaluated as J1. Okay, this is sorry, I need to be sure about this. This is J2, J2 on the right side. Sorry for that. This is J1. Oh, sorry. Okay. this J1, this J2, this J3, this J4. Every Jacobian matrix here has its corresponding number of rows and columns, which is dependent on a formula that I will discuss in the next few slides. But again, it can be represented by simply by having this relationship. Ito yung isosolve natin, itong mga ito. And this one can be computed on the problem itself. Ito yung unknowns. Okay? So in that case, we can have that relationship as in using this matrix. Simple as this. Okay, I can this matrix here. Okay? So the elements of the Jacobian matrix are the partial derivatives I have mentioned. So I already have a platform here of J1, J2, J3, and J4, and it is evaluated at delta V and delta rho, that angle. Please take yung angle of the voltage yan, ha? Ito voltage magnitude. For the voltage angle, voltage controlled buses, please take note you have some parameters here later. Yung N at saka yung M. Ito yung bus, number of buses. Ito, number of your voltage control bus. You already know what is a voltage control bus because we have discussed that on our Newton Raphson, not Newton Raphson, Gauss-Seidel solution. And then if there is a m number of buses that are voltage controlled, the equation of delta P and delta Q and the corresponding columns can be eliminated now, so hindi yan mabubuo, and it will be further simplified in terms of a matrix. Okay, let us move forward to this. Please take note of this equation, the number of elements that you can consider on the Jacobian matrix. I will have this on a separate annotation here. The matrix of the Jacobian matrix, Jacobian matrix, is a 2n minus 2 minus m by a 2n minus 2 minus m matrix. So it depends on the number of buses and the number of voltage control bus that is given. So it can be 3 by 3 square matrix din siya kung tutuusin. It can be 3 by 3, 4 by 4. As you can see, they are the same, row and column. Diba? Alam mo naman, row and column, right? So in this case, you can evaluate as well the number of rows and columns of J1 and J4. Please take note of this. What is J1, J2, J3, and J4? It will depend on the partial derivative. Ito, real power yung numerator, but it depends on what partial derivative. Ibig sabihin, isa dyan is constant while the others is being changed, right? So you already know that one. So ito J1, ito J2, this one is J3, and this is J4. And this J1, J2, J3, and J4 has its particular rows and columns. So J1, N1, N1, J2, N1 times N1 minus 1 minus M, J3, N minus 1 minus M. Sorry for this. Yeah. So, ito naman siya sa J3, and ito naman sa J4. Ayan. So, please take note, they have this number of cells, or number of elements on that particular J1, J2, J3, and J4 matrix. But as a whole, it is this. Yan. 2 minus 2, 2n minus 2 minus m times 2n minus 2 minus m. Okay, now, later you can have an idea about this. But as long as you can see, yung heavy math, yun lang yung medyo tedious dito, the solution. Kaya nga, it's very faster siya, but again, the process mechanical naman. Kaya nga yung harder part on this case is the tedious calculations, which is expected for a Newton Raphson technique, which involves Jacobian matrix. Okay, now let's move forward. Okay, now ito yung sinasabi natin that you can get the partial derivatives of every elements. You have the diagonal and the non-diagonal. Okay, this is the diagonal and the non-diagonal. And you have the partial derivative using this formula here, as you can see here. So may formula na siya na naka-designated, and this is designated here at J1. Okay, this is equation 8. You have also the off diagonal and diagonal elements of J2, which is have on this type. Okay, ito yan. Okay, you can use this formula, no? And then you have your J3, no? Which is this one. You have your off and diagonal. Ito, yung you have your J is equal to I. This is your off diagonal. And this is your diagonal here. As you can see, they have the same pattern, no, on P. As you can, we go back here. They have the same pattern. Nangyari lang, naging cosine lang siya. Okay, you can see it if you observe it carefully, no? Ayan. And last but not the least, no, for the J4, this is not equal to J2, no, because they are different. But yung, please take note of the J1 and J3. The only difference is the cosine and sine. And this is for the diagonal and the off diagonal for J4. The formula directly, no, for using, no, the partial derivatives of Q versus the magnitude of V, which is constitutes to J4. Okay, now those are the equations. It's already made, but again, we can also have a review for that, no, on a certain problem solving, no. So if you want to have, no, some references on where I get this one, you can consult the book of Hadi Saadat, no, Power System Analysis by Saadat, no, a very good book, no, for this topic. Okay, where I get the majority of the lecture for LF, for Newton Raphson. Okay, now the terms of delta P and delta Q, no, from what we have, no, on equation number 6 can be solved, no, by using this equation here, no. So delta P is parang walang pinagkaiba, no, on the on your Gauss Seidel, di ba, yung new minus old value. So ito siya, scheduled minus yung this is your old value minus new value, old value minus new value. Okay? Parang K is the preceding iteration. This is the old iteration. So this is called the power residual, the change on power, which we will discuss, no, on a sample problem. Don't worry. But we have the algorithm itself that I can present to you in the next few slides. Okay, next, no, we have the new estimates, because this is the parameters that we need to solve, the voltage per bus, and you can use this relationship. Parang old minus old plus new ito eh, di ba? And then if you have the tolerance error, no, we can have this as 0.00001. If it achieves the tolerance error of 1 times 10 negative 5, then you need to stop the iteration. Like, ano rin, like your Gauss-Seidel method, right? If you achieve the tolerance method, then Viola. If you achieve the tolerance method of this one, you can end up the iteration. Then it is already convergent. Okay, now we can erase this part. I will not erase the right side because later it's very important to us that we have that guide, no? Okay, this is the algorithm that I'm talking about to you. Just read this out. But again, no, the most important here is like Gauss-Seidel, you need to have an assumed value of your voltage and the angles, no? In this case, the voltage, no, aside from slack bus, which is 1 bar 0, no, is assumed to be this. The voltage at V2 up to Vn is 1 magnitude, and the angles, no, from V2 up to Vn, the angle, kasi alam mo naman, V is V magnitude angle, right? So we can assume that is 0. So yan lang naman ang assumption. Basic assumption before you start the solution. You can use any number, but it is more practical that you start at origin at 0. Okay, now it will depend if that is a load bus or a PQ bus, no? So it can calculate, no, the change of power, which is this one. Ayan, yung power residual, no? From 3 and 4. And then you can calculate from delta P and delta Q from 12 and 13. We have no that equation later. So no worries about that. No, so we can have no a sample calculation, and then you will know the ones who will follow up. And then the for voltage control bus, you can compute no those no power residuals from 3 and 12. So just we will follow. This is also the same thing that we will do on the sample problem. Don't worry. I just generalize this one as a step-by-step procedure. Then number 4, no, the elements of the Jacobian matrix can be calculated no from equations 8 to 11. Itong mga na-compute natin kanina, ayan yung mga yan. Okay, 8, 9, 10, 11, but we will repeat that no on our problem solving no on the next few slides. And then the linear simultaneous equations from 6 can be solved optimally by considering the triangular factorization or even Gaussian elimination. Itong equation number 6 kanina yung may delta P, delta Q, J1, J2, etc. I think this one. Ito to. Since all of this no are already given, you can now get delta your angles and your voltage here by using matrices, no, yung Gaussian elimination, factorization, LU factorization. You already know those techniques no from your advanced math. So again, you need to have no the foundation of that because this is very important on this algorithm. And then no you can now get the value of the voltages and the phase angles computed from 14 and 15, and you need to know no the residuals if that is less than no from the specific accuracy. So it means guys no may ano tayo no if you have the new estimates here, so check it on the power residuals by using your tolerance error, right? Which is 1 times 10 negative 5. Okay, I think much better that we can have no sample problem. So please bear know what we have discussed so far, and then from there, no, from the formulas that we have, we can now substitute it here, no, on the problem. Please take note of the values of the magnitudes here and whatever the number of buses and the number of voltage control buses. Okay, let us have we need to read the problem first here. This is problem number 4. No, the continuation, no? Kasi problem number 3 tayo last time. This is problem number 4 for Newton Raphson. Figure below, no, has an SLD, no, of a simple 3-bus system, no? Okay, which has 2 generators, which is bus 1 and 3. Okay, bus 1, no, can be a slack bus. Okay, it's already given here. Always remember, bus 1 is a slack bus, so that the solution is in ascending order. Ang susunod naman is V2 and then V3. Hindi pwede na V3 yung slack bus, tapos V2, V1. So to avoid confusion in terms of the numbering, and so the same process, your slack bus must be bus 1. Okay, it is 1.05 bar 0. It means that this voltage here is forever. Huh? It's because it's already given na eh. What it is important is how can you compute for the bus voltage here and the bus voltage here as well, using the technique of Newton Raphson. And if you already know those voltages, you can go back to Gauss-Seidel method in order to get no yung mga ano to 3-2, right? Yung power yung current flows mo, 'di ba? Yung mga yan, you can still recall. There's an equation here using Poisson IV, using nodal. You can go get that currents there. And then from there, you can already compute for the slack bus power, the power at bus 2, power at bus 3, etc. So which you can compute as well dun sa delta P. But anyway, you can get the current flows, and then you can get the power flows as well using the method of Gauss-Seidel. So you can go back to what we have started. But this is just a different method in getting the voltages of the magnitude and the direction using Newton Raphson. Okay, now we can erase some of the unnecessary annotations here, but I just clarify these things up so that you can appreciate. To those who already view the videos on my YouTube channel. Now, in this case, meron ka raw VCB 1.04 at bus 2. And please take note that the power generation is 200 megawatt. A load consisting of 400 and 250 megavar and megawatt 400 is taken from bus 2, as you can see here, from this PQ bus. The line impedances are marked in per unit already in admittance na siya, no? So these are series admittances. Obtain the power flow solution using the method of Newton Raphson as we have described so far. Okay, now, please take note of the following assumptions before we take into account this algorithm. Okay, now I did not mention here, how about if the problem has Q limits? Okay, that will be another different algorithm if you have a Q limit. But to simplify things out, just to present what is Newton Raphson all about, there's no Q limits on your voltage control bus. So that's why I already mentioned here, there's no Q limits on the VCB. Okay, so just give you a feel on how it is done, no? So if there's a Q limit, there's another algorithm that we will not tackle on this video lecture, but I think on another session. Okay, now also it is assumed, as we have mentioned a while ago from the procedure, that you have your voltages magnitude as 1 bar 0 for V2, since V3 is already has its value forever on the voltage control bus as 1.04, and the angles as mentioned as delta 2 this rho 2, and then this is rho 3, which is equal to 0, o yung voltage angle. So ang sosolvin natin, by the way, is the new value of V2 and the new value of the bar angles. Please take note, the magnitudes of V3 and V1 at saka yung value na rin ng slack bus is already constant. So constant na yan. The parameters that you need to compute is this 3. Because voltage control bus, pag ibig sabihin ng voltage control bus, is already constant. Whatever the changes on the system, that voltage must be controlled up to 1.04 per unit. There's no changes. Okay, now let us erase these parts here and then go to the algorithm itself. Okay, now let's move forward. Now this is an assignment. Your problem set number 3, problem 3. Because problem 1 and 2 is already on Gauss-Seidel, right? Problem 3 and 4 will be on this video. You need to determine the admittance matrix of this. So we already discussed this one on video number 3, on problem number 1 on Gauss-Seidel, right? So if you have your admittance matrices, series admittances here, so create this admittance matrix, which is very important on our calculations. Okay, now we will make use of this as our data for our solution on the next few slides. So please take note, this is your working assignment. Okay, now the first step is you need to convert this matrix here to its corresponding polar representation. However, this one here, as you can see, the angle, okay guys, the angle here must be in radians. So dapat naka-radian yan. Di ba kanina may value kanina na 20 minus J50, Di ba? So to get the Y bus there, dapat iaano mo siya, convert mo muna siya sa polar. And then the angle, ito, as you can see, go back here. I think this is 20 minus J50, right? 20 minus J50. In your calculator, this is 20 minus J. This is just an example, and you will do it on the next element, on the other elements. Convert it to polar. So it will yield with 53.8516 bar angle negative 68. But this one is in degree, right? So the problem needs us, so that it can tailor fit with the equations, it must be in radian. So to convert it, you need to multiply it by pi radian over 180 degree. And the answer in radians is 1.19. So ito yan, 1.19029. And do the rest, no, of the elements. Okay, next, we need to erase this again. So I have the step-by-step procedure here, but the math and how you will calculate it one by one, it's your sole responsibility already, because what is important is you already know the method, the calculation and the math there, no, it's already yours. No, you need to know the procedure itself. Okay, now we have this. So this is 50, the same thing here. Do the next elements on your own. Okay, next. From equations 3 and 4, no, from what we have, no, this one, no, so you can see here, we need to derive the expression of the real power from bus 2 and bus 3, no, and the reactive power at bus 2, no, which is this. Ito lalabas, ano? This is your P2, just substitute up to, no, 2 here, and then it will yield with this relationship, no, here, no. Ayan po, in terms of cosine. So this is from equations 3 and 4, no, of the power at real bus 2 and 3. Ano itong equations 3 and 4? So just go back many slides, no. This is what we have discussed so far. So you can see these equations here, okay, which is we separate real and imaginary parts. And if you do this, the math here, it will yield with this, no, relationship. Ito, ayan, ito to. Okay? So nakaano ito, no? From bus 1 to bus 3, since tatlo ang buses mo eh. So do that and it will yield with this relationship. You will also have P3 because at bus 3 naman tayo magsisimula, and using this equation 3 here, this is equation 3 by the way. And if you do this, it will yield with this. And you have only, no, have this one in bus 2. Ito kasi bus 2 and bus 3 may real power eh. Diba? Kasi may voltage control bus ka, tapos yung isa naman may PQ bus doon. Ngayon, yung Q2, which is at bus 2, do the same pattern there, it will yield with this relationship. Okay? So again, it's already expressed, no, by using these equations here, which is equation 2 and equation 3, which is very important in getting the power residuals later. Okay? Kasi nakadepende yan sa connections mo dun sa power system. Okay, let us move forward. Okay, if you already have this one, alam mo na yung susunod dyan. Ang susunod mo dyan is you need to partial differentiate now P2, P3, and Q2 to its corresponding, ayan, voltage angle at saka voltage magnitude. You need to have the partial differentiation of these three here, no, with respect to the angle and with respect to the voltage. By the way, this is partial derivative. May kulang pala ako. So dapat may partial pa dito eh. Ayan. Anyway, it is already understood na rin. Sorry for that. Partial derivative or P2 with respect to angle 2. Okay. I think that is already na. Yung rho na yan. Okay, now if you do so, I will not go to the math details so that we can conserve the time, but I want you to understand this fully because this is one of your problem set. What will happen? You will have the J element matrices, which is equal to this, the J1 element matrices. If you partial derivative P2 with respect to the angle 2 of this equation, ito, this equation here. If you do this also for P3, no, P2 and P3, and then Q2 in terms of the angle and then the voltage magnitude, then you can now have the elements of your J1, J2, J3, J4 respectively. So you will do the same thing with P2 and P3. As you can see, that will be your J1 elements. Basta with respect to angle 2, that is J1. With respect to magnitude of the voltage, that is J2. Kaya nakalagay dito, J2 element matrices, J2 element matrices, and J1 element matrices. Also for Q naman, no, for J3 element matrices, for with respect to angle, and then this is for J4 element, that is only one for the voltage. As you can see, no, the formulas that we have here, as you can see, no, from the elements here, is already derived, no, from equations 8 to 11. Ito yun. Ayan, no. Look spam yung may 2 rito, oh. This is for J3. This is for J2. And this is for J1. As you can see, the only difference din pala, no, as you can see, is cosine and sine, no, for J2 and J4. Ayan, napansin ko rin pala. Okay. But anyway, there are some similarities. But as long as you know that formula there is already consistent on what we have already derived on this problem. So, ayan na rin po yan. Okay? So, since we already have the formulas for J1, J2, J3, and J4 element, if you can still recall equation number 6, we need to get the power residuals. So in order to have the S2 and P3 relationships here, no? So which is S2 is in terms of P and Q, no? Ito na yung P2 saka Q2 respectively. Okay? Ito given ito. Ito yung MVA base. 100. So ayan yung MVA base natin. So lalabas is ito na yung sa P3, P2 saka Q2. Ito na yung mga yan. Yung schedule. So ayan na yung mga values na yan. The question is, paano nakuha itong tatlo? Yung mga yan. Okay, I have a sample equation, yung nga yung sa equation 2 at saka equation 3 kanina, no? At saka we developed that already. So just substitute all of the parameters on the problem there, then you can get that value. So anong ibig sabihin yan, sir? So paano mo, how did you get those values? Okay, just recall again of equation 2 and 3, no? The phase of that equation, this one, as you can see. Just substitute all of the parameters here. And the angle is already defined in regions. Please take note. So that's why from the Y matrix, we change all of the parameters there to regions, right? Okay, now let's move forward. So in this case, moving forward now, how did you get 1.14, 0.56, etc.? So one sample problem. This is from last slide, slide 24, if not mistaken. So the formulas for P2, P3, and P2 and Q2, we have this formula for P2, right? The parameters of V2, V1, and this one are already given on the problem. How about your Y21? This is from the Y matrix. All the parameters here is from the Y matrix. One sample. How did you get 22.3608? So Y21. Bar angle means magnitude, ha? Alone, magnitude lang. Because the angles are already mentioned here. Yung theta, kanina, as I mentioned, is the angle of Y. Alpha, o yung rho, is the angle of the voltage. Okay, move forward ulit tayo. O move backward. Dun sa Y matrix, Y21, no? Row column lang yan. Okay. I will erase this one. Okay. Y21. 1, 2, 3. 1, 2, 3. 2, 1. O, see? Ay, Y12 ata ito. Y12, kaya 22.2. Y12 ba yun? Dali 8. Say Y21 is 53. Y12 is 22.36068 ito. So diyan lang nakuha yan. y12, y21. So depende kung ano ito ha. Kung y21 yan, y12. So let us check. But that is magnitude of the y matrix. So if there's some wrong on my on my type, so please bear na lang sa akin. So ito ba? Oh. So I think there's some changes dito, no? 35 point. Basta galing 'yan doon, no? So just please check this. But the answer here is 1.14. It will no be no on the Y matrix, no? So yung 2258.1337 tama eh. 22 pala ito. Sorry. 22 to. 22. Yeah. Correct pala, correct. Sorry. Mali ako ang may mali. Look. Again. 1 2 3 1 2 3. So 2 1, ito pala dapat row column 2 1 2 1. Yeah. So the answer is 2 1 to 2 1. Sorry, that's correct. Okay. 2 1. Yung isa naman y22 magnitude 2 2 2 2. Ayan. Ay, sorry, I mistakenly. I think I already, no, I need to have my lunch already. Nagugutom na siguro tayo. Ayan, tama. This is correct, no? 22.36068 para dapat kasi mangyari. As you can see, the Y matrix, as I mentioned, is a square matrix. So if that is a square matrix, Y12 is also Y21, Y31 is equal to Y13. As you can see, one sample is Y13, 31.62 is equal to 31. Okay, anyway. 1331. Okay, that is already correct. Okay, let's move forward. Okay, now if you already have those values, no, just substitute on our equation. And then it will yield, oh, what happened to this? Meron ako kanina dyan. It will yield to this, no, as 1.14. Okay, as 1.14. So apply it to P3 and Q2, it will yield with 0.56 and negative 2.28 here. Okay, already done. Okay, let's move forward to some sample problems. No? But before we proceed, no, with anything else, what is the expected, no, matrix on this problem? Since you have n is equal to 3 buses and you have an m is equal to 1, the expected, no, matrix is a 3 by 3, right? So n 3 2, 3 times 2 6 minus 2 is 4 minus 1 3. 3 by 3 matrix. So you will expect, no, the overall matrix here is a 3 by 3. But what is the, no, the Jacobian matrix on the 3 by 3? One of them is a 2 by 2. Ito yan, G1. One of them is a 2 by 1. 1 2 1. So you have two columns, no? Isa is 1 by 2. So ibig sabihin you have one row, two columns, no, naka-vertical. And then you have a 1 by 1 dun sa dulo at J4. Later you can see that, no, on our computations. But how did I derive 2 by 2, 2 by 1, 1 by 2, and 1 by 1 here? No, on the number of elements. Okay, basta ang mahalaga, we already know that is a 3 by 3 element. But again, this is the elements here that we have discussed, and this is the Jacobian matrix. But we can have, no, the values of the Jacobian matrices based on the equations that we have already kanina, no. So ito yung mga yun. Ewan ko ba't nawala, no? But we discussed that one a while ago. Yung J1 element matrices, ayan. Ito, no? Saka ayan, nandiyan na lahat. J1, J2, J3 with the corresponding formulas, no, based on the partial derivatives. Now we can have, no, the first three rows here. So, unahin muna natin dito as a sample computation. You can get the partial derivative of P2 and alpha 2, which is this at J1. Using this equation a while ago, all of the parameters is already given plus the Y matrices. Diba? Please take note, on our Y matrix, the angles must be in terms of radians. So in this case, pero guys, no, we make use of radian. Pero sir, bakit mo binalik sa pi? Because on my calculator, no, in order to have a sign, it must be in degree. So please take note. By the way, I forgot to mention one thing. No? Here, you can have radians or pi or degree, but again, I make use no to have in degree again. No, kasi on my calculator, it accepts radian or degree, but I use degree because on the book of Saadat, he used radians. So it's your discretion naman eh. I go back to degrees again, radian or degree. Basta importante, you have the same unit. Then in your calculator, you can use your identity in terms of degree or radian. That's the wrong on your calculator eh, if you want to have in radian or degree. Now, I use the Y matrix in radians and in degrees. As you can see, we have two Y matrices kanina kung nakapansin ninyo eh. But again, the solution will be the same thing if that is degree or radians eh. Ito is naka-radian dito. But if you want to go mo degree, walang problema. Basta you're consistent on your calculator, ha? No problem yan. So, again, here I use degree. Binalik ko rin sa degree so that I can be consistent on my calculator, no? So that you can see the answer there will be approximately 1.14. Okay, now let's move forward to this, no? So you can see here, no, this is the equation. Then I substitute all of the parameters there. I can erase this part, parameters there, and then it will yield with 54.2806 magnitude. Now we can also compute for the next element, no? Ito naman yata is yung non-diagonal element, no, the second element on J1 using this equation a while ago, and then substitute the values here, and I have it in a degree value instead of radian in my calculator. Answer is 33.28 negative. If you want to get the next row from P over V2, all of the formulas again is already given from the past few slides. Just substitute as a sample calculation. The answer is 24.86. Now, if you complete all of the 9 elements based on the equation here, as I have mentioned, 9 yan, no? 9 elements, 1, 2, 3, 4, 5, 6, 7, 8, and 9, no? The answer will be, or the answers, the next few answers will be this. Ayan ang lalabas. As you can see, you have 9 elements, 1, 2, 3, 4, and as you can see as well, what we have discussed, this is a 2 by 2. Okay? This is 2 by 1, 1 by 2, 1 by 1, which constitute J1, J2, J3, and J4 elements, right? Which is this. Okay, now, the power residuals, ito na yung delta P saka delta Q kanina. Ito yan. I think this is delta P, ito delta Q, which constitutes as well with this relationship. I just have a broken line here based on the Jacobian matrix that we have on equation number 6. Okay, now, hindi pa tapos yan kasi kailangan nating i-check pa doon sa error tolerance. So we can clear all the drawings here. Oh, sorry. Okay, since we already discussed that Jacobian matrix. We can have the error tolerance here. Yung 0 kanina, 0 naman yun eh. Tapos yung voltage is equal to 1, no? So ito yan, dito yan nanggaling yung mga values na to. Okay, and this is the initial value wherein you can now get this angle here and this voltage here by using matrix. Ito yung sinasabi nating factorization, LU, Tapos Gaussian elimination, you have a 3 by 3 matrix here. You can solve these values here. And the values that you already solved, no, from the above equation is this. And then get, no, the tolerances. Since ito hindi pa na ano, no, the new value rather of your alpha, rather the scheduled value of the next iteration, ito yan. Okay, yung delta P sa delta Q yun na magdedetermine ng iteration in the next slide. But again, do the matrix solution of the second iteration. So ito naman ang mga values for the second iteration check. Okay? So in that case, no, for the second and third iteration, ito na ilalabas. Ano? And if you do it, no, ito sa ano, no, sa third iteration. I did not cover the second iteration because that will be your working assignment. So go back, no, to the book of Saadat. Then you can see, no, some of these calculations there. I think the value of the second iteration will be given, but again, I want you to practice that out, and you must have the same answer. And thus, no, as you can see here, you can now have the power mismatches, no, from converge in three iterations, I think. Okay, and I forgot to mention the power tolerance, no. Doon dapat mag-close yung solution, no. You will be continued, the process will continue until you reach, no, the power residual at 1 times 10 negative 5 or 0.0001. If the delta P and delta Q reaches to this level, okay? Since we stop here, no, yung pagkuha ng voltage angles, but you will stop the solution if it reach the tolerance level of the delta P and delta Q, huh? Okay, now in this case, this is the solution in terms of the Newton Raphson. It will yield with 3 iterations. And I solved it by using computer, no, yung ano, by using my algorithm in MATLAB. In Gauss-Seidel, it reaches at least 12 to 12 or 13 iterations. So, akalain mo 13 iterations before you go, no, with these answers here, which is the same eventually. Okay, so the expressions for the active powers at bus 3, no, you can use, no, these equations based from what we have on equations 3 and 4, no, to get the values of P1, Q1, and Q3. Kasi given na yung P2, di ba? P3 at saka Q2, no, doon sa calculations. And it converges to 3 iterations. And thus, no, upon substitution, we can have the final values in per unit. And if you already have all of the values of your voltages and bus powers, you can now calculate the line flows using the method of Gauss-Seidel as mentioned a while ago. Okay, I think that will be enough, no, for the conclusion of this topic. Okay, thank you very much. Now we can stop the recording here. And please take note, by the way, your problem sets, no, your problem on your problem set. This is problem number 4. You need to do the solution to the second iteration. And then, no, the another one, problem set problem 3, is the Y matrix, no, in terms of radians. Okay, now in this case, in terms of the angle in radians. So in this case, guys, no, this will end our video lecture. Thank you very much for listening. Okay, we'll stop this one.